the work I'm going to be talking about today is really the main person behind it is Eric Weitnauer, who is depicted on the left. And I'm going to be talking about work which is really the basis of Eric's doctoral dissertation at University of Bielefeld back in 2015. But since then, we've continued to do experimental human work on the model that he developed. He is currently in Bloomington, Indiana. He's the CEO of a company called Graspable Math, which actually builds on and extends in very different ways the work that he was developing in his doctoral dissertation. Perhaps at the end, we can talk about how what he was doing back then has, through the alembic of time, has turned into work on how to improve mathematical reasoning among algebra students. So, and the other person is Helga Ritter, who is a professor at University of Bielefeld. And so what at a high level we're trying to do is talk about incorporating perception into the process of category induction. And it probably won't come as a surprise to most of you in this room that many models of category learning are treating perception as separate from and completed before the processes that represent and use concepts, right? And I included one of my models in here just to show that I'm not trying to pick on people. It makes perfect sense to do this. It's hard enough to try to come up with models of category learning without also handling the perception problem. However, I'm going to be arguing that it is a distinct hallmark of human cognition that oftentimes we are able to change our perceptual descriptions on the road to coming up with new useful concepts or categories that we need to build. So I believe that there's some aspect of human cognition with its deep roots in creativity, which would require us to continue to try to come up with new descriptions of the objects that we're trying to categorize, rather than treating the initial representations of the instances we're trying to categorize as already built in. Okay, and so there is literature in artificial intelligence that sounds like it's doing exactly this, which is interested in creating new descriptions in order to learn a category, in order to induce what is a category given instances that belong in the category. And this field back in the 90s and 80s was known as constructive induction. And constructive induction as a field of artificial intelligence does indeed create new descriptions, but in a rather disappointing to me, a rather limited sense of Boolean expressions, so that if you have a description of an object as square and another description as black, you can combine those together to create a description black and square, or black or square, or black if and only if square. But these are the kinds of new descriptions that a lot of the early work in constructive induction was creating. On the other hand, there is another literature that really does create internal representations known as deep learning. And these are multi-layer networks where through massive training with lots and lots of examples, you can create new internal representations that are exactly going to be useful for categories that need to be acquired. But as Brendan Lake and other people have observed, oftentimes these deep learning systems require a massive amount of training, whereas people do not require a massive amount of examples in order to induce rules. There is a current work of note in deep learning worlds that are trying to get away with few shot learning or one shot learning or sometimes no shot learning. But many of these systems still require a huge ton of pre-learning in order to get to that stage. Okay, so what we're going to be arguing for is building perceptual descriptions for entities, noticing new perceptual qualities while category learning is going on, while you're trying to figure out what is the category, what is the nature of the category of all the instances on one category that connects them together. At one level, what we're going to be talking about is definitely reminiscent of work that I did decades and decades ago with Doug Medin and Dedry Gentner, showing that it would be convenient if you could first say that when you're doing a comparison process, you list all of the features of one object, you list all of the features of the other objects, and then you compare those sets of features in order to figure out how the objects are similar to each other. Unfortunately, that doesn't work because the comparison process itself brings up new features that you hitherto had not considered for the objects that you're comparing. So in the example that I'm showing on the screen here, when the object in the middle is compared with the object on the left, people say that a commonality of both is that they have 3 prongs. Now, if I compared the objects on the right, people would say a commonality of both of those objects is that they have 4 prongs. So you have mutually exclusive descriptions of that middle object, depending upon whether it's being compared with the object on the left or the object on the right. And so that puts limits on this idea that you can first create all of the featural encodings that you need for the objects before they enter into comparison. Comparison produces feature descriptions at the end. We're going to be making exactly the same argument, but in this time, there's going to be far more objects that are going to be compared. Okay, to flesh this out a bit more concretely, our task domain is going to be the same domain that Melanie Mitchell talked about in this analogy colloquium series last semester. She was talking about Bongard problems as a great domain for looking at people's open-ended creative ability to create new descriptions for scenes. Okay, and other people have made exactly the same argument. Shimon Edelman has, Stephen Piantadosi has recently. So the task for people solving a Bongard problem is to look at the scenes on the left. There's 6 scenes on the left and there's 6 scenes on the right. And you're trying to come up with a rule that will allow you to categorize, allow you to sort the scenes into either the left category or the right category. And I'm looking at the chat window. So this is an easy problem. Somebody type in, please, what the correct answer is. What is the rule that allows you to distinguish them? It's Bongard. Excellent. Alex got the correct answer. So there are objects that are small. There exist small objects on the left, but not on the right. So Michael Bongard was an early artificial intelligence researcher in the 1970s who came up with a number of these problems. He didn't have any model that would solve the problems, but he came up with the problems as an interesting domain for category induction. They were popularized for many people by Doug Hofstadter in his book that changed my life, certainly, when I read it in high school, Gödel Escher Bach, where he introduced a number of his own Bongard problems. And there is now a small cult following for Bongard problems where people are sharing them, people are creating new ones. Harry Fondellis was a student of Doug Hofstadter's, and he did have a computational model that solved a small subset of Bongard problems. Okay, so that is what the task is. Let me try to give you another one because Alice got that one very fast. So here's another example of a Bongard problem that I would treat as fairly simple. So first person to get the answer gets a prize. they get the knowledge that they were the first, I guess, which is their prize. So what is the rule that distinguishes the left side from the right side? Joshua, yeah, got the correct answer. On the right side, we have a small black circle, or you could just say a black circle. And on the left side, we had a triangle, a black triangle. So this would be a standard conjunctive kind of rules. And now, so far, you might think, oh yeah, I can easily imagine that people are thinking about the objects in these scenes in terms of their shapes and colors. Okay, so, but the interesting aspect of Bongard problems is it's not always so easy to think ahead of time about what all the features of relevance could be. And so I'm going to give you 2 examples of that. Here's one of them that came to us from Mikhail Bongard himself. So can somebody give us a rule for why the 6 objects on the left belong on the left and the ones on the right belong on the right? Or just half of that rule would be fine too. And so the point of these Bongard problems is you're probably going to have to come up with a new description of these scenes that you hadn't thought of before in order to solve the problem. Yeah, good. So Tom got the answer correct. Yep, and Max got it right after him. Very good. And those are older individuals with less crystallized or less fluid intelligence. So congratulations. So on the left, the endpoints of those curved figures are parallel to each other, whereas on the right side, the 2 ends have orientations of 90 degrees somehow. And so that is probably something that Tom hadn't thought about before. So Tom wasn't originally looking at one of those objects and thinking about that, but then somehow during the course of making all of these comparisons, he comes up with that. And so that is the exciting kind of creative human ability that we're interested in modeling. Okay, and finally, one last one to make a conceptual point. This one comes to us from Doug Hofstadter, my colleague and collaborator here at IU. And this is a somewhat tricky one. And the reason why I want to present it is because it makes the point that oftentimes when people are trying to solve these problems, they need to create new descriptors that they hadn't created before. So they might add lines, or they might think about how these objects would move, for example, something like that. That would be true for our system. So people are still thinking about this one. The other thing to make a conceptual point about these Bongard problems is you can get plenty of complexity in these problems, even though you only have a few elements, right? So there's only 2 elements. There's only a line and there's only a dot in each one of them. And yet they can be quite complicated, rich to solve because they are embedded in these spatial worlds. And there's so many different things that can be read off of space. Okay, so I might give you a help. So I added something that you could have added yourself to the objects. There's no real additional information that I've added here, but it might help some people solve this as a puzzle. Okay, I'm going to give you this answer then. So the answer to this puzzle, which is pretty hard, is that all of the triangles, if you were to form them on the left side, would have been isosceles, and all of the ones on the right would have been scaling. And what scaling means is that all of the lengths are unequal to each other. Okay, great. So that's what Bongard problems were. And just to make a conceptual point, which is that this is not just a game to entertain nerds, but it is also fundamental to understanding in mathematics and science. For example, in an earlier pandemic in 1854, cholera was spreading in London, and John Snow had to consider a hitherto unknown, unthought of description of what would predict whether people belonged in the category of those who would contract cholera or not. And that was their proximity to a particular well, right? So people who were close to a particular well and were getting their water from the well, which is a new description, is what was a great predictor of whether they would get this disease. And maybe even a more amazing example comes to us from Maxwell. When he created kinetic molecular theory, he sees pressure. He has devices that can measure pressure in a particular vessel that contains a gas. And what he ends up inferring, the new description that he ends up creating, is something about these invisible gas molecules that are bumping up against each other and bumping up against the wall, right? So it's amazing that he is able to create this along with a whole litany of other scientists at the same time. He's able to come up with this very new description in order to categorize different events in terms of the pressure that they will exhibit. Okay, so these are real world examples that our system will certainly be not capable of doing. Eric Weitnauer has an interesting modification or subset of Bongard problems that he is interested in. And these are called physical Bongard problems because they require for their solution that somebody imagines that these objects are actually physical objects that are subject to physical forces, gravity, collisions, support relations. And in order to solve this problem, maybe I'll just give you the answer here. The answer to this problem is that if you were to mentally simulate using an internal physics engine in your own mind, then you would be able to infer that the left scenes all have objects that will end up touching each other once the system achieves an equilibrium state. And on the right scenes, the objects will not end up touching. Sometimes they may collide with each other, but they will end up in an equilibrium state without any touching behavior. And it's been observed by a number of recent scientists, cognitive scientists, such as Kelsey Allen, Josh Tenenbaum, Peter Battaglia, Tomer Ullman, now at Harvard. It's been observed that people do seem to have some ability to simulate what an event would look like if it were to have a physics engine underlying it. And I'm not going to be arguing that our internal mental physics engine is realistic. I think there's probably interesting ways in which it differs from the way that physics works out there in the world. But at a first pass, we can explain a lot of how people are able to make novel inferences by postulating that they do have some ability to entertain physics. Okay, and simulate those physics. And so from our perspective, what adding physics to Bongard problems does is two important things. First, it makes the important conceptual point that one reason why we don't start with all of the descriptions for scenes preloaded into the scenes, but they're built up gradually over the course of trying to solve a problem is simply, practically speaking, there's too many descriptions that could be run. Physics simulation is a costly simulation to run. You won't run it unless you feel like you have to run it. So by making these problems physics-based, you bump into the natural cost of creating a new description. And so that's something, it's easy to imagine with black squares that you just immediately get that. you could imagine that's being done very, very quickly before you start comparing objects, before you start comparing scenes. But in the case of these physical Bongard problems, things are too costly. You can't compute all of the combinatorial explosion of different spatial relations that are involved in a physics simulation. The second thing it points out is that in contrast to constructive induction, which I presented before from artificial intelligence, it's clear that the descriptions that are coming out of a physical simulation are not as trivially embedded in the description that was originally presented. You have to engage in this, well, for us, a black box of a virtual physics engine that you're running in order to read off different interpretations, but they're not going to be built in. You need to have something like a perceptual simulation process. Okay, so that's why we are particularly interested in these kind of Bongard problems. So, okay, so paths is the name of Eric Weitnauer's computational model, which we've compared in different ways to how humans solve these problems. It stands for perceiving and testing hypotheses on structures, and it's a crucial component of paths that the descriptions that it's creating for the scenes are context dependent in several important ways. One of the ways that these descriptions are context dependent is because your threshold for calling an object by a particular attribute name is going to depend upon the rest of the scenes that it's being compared to. So you have an adaptive threshold for saying that two objects are close to each other, or that one object is big, or that one object is left of versus above another object. So Eric started by using Isabelle Bloch's way of having a logical fuzzy representation for spatial predicates like left, right, above, below. And you can see the fuzziness in the descriptions that we start off with for things like left of and right of, because how well something is left of is going to be shown by how bright the area is. So if we're talking about this landmark object of this horizontal red rectangle, then the things that are right beside it are going to be the best left ofs. But as you kind of go up a bit, it's still left of, but it's not as good a left of. And the way these are computed is just by integrating over all of the different bits that make up this landmark object, and then seeing for all of those integrated bits for each part in space, is it true that the object is literally left of the object? Now, we use these representations in order to derive conjunctively different kinds of higher order spatial relations. So the notion of support, for example, object B is supported by object A if B is above A and if B is touching A. So that would be how we have a conjunctive representation for something like support. It doesn't completely exhaust support, but it's okay for our first pass. We also find that it's useful for putting these opposed spatial relations in contrast to one another. So our better representation of right turns out to be what is the representation for right, which is in the middle here, and we then contrast that to the representation for left. And so things that are both in left and right, they are not going to be good candidates for being in our eventual right representation. So our improved right representation is going to be understandable as the right area minus the left area. All right. And in a similar way, you could say above is going to be represented in terms of the absolute position of an object, but also in terms of the intersection between left and right. So that's how we're going to think about building up these fuzzy representations for objects. And one kind of flexibility that the system has is saying how much evidence do I need to call a particular relation or a particular attribute what it is. So another kind of context dependency within paths is that descriptions that are frequently given for the scenes in a category will tend to be tested on other scenes from that same category. So once we have a selector, as Eric calls it, once we have a selector, which is going to be describing something in a scene, that is all of a sudden going to be weighted as something that would be tended to be looked at for other scenes. So this is true for all of the scenes that make up like the 6 scenes within one side of a Bongard problem, but it's also going to be true in a more immediate sense for the scenes that you're comparing at any given time. So a lot of what we've been doing for our human subjects is trying to change the difficulty of a Bongard problem by pairing the scenes that we ask people to assess, and we pair them in different ways that will either help or hinder them from seeing the underlying solution. So that is the final thing that we're trying to get at, which is this immediate either temporal or spatial context, so that you're going to particularly attend to similarities in adjacent scenes if they come from the same category, and you're going to tend to dissimilarities between 2 adjacent scenes when they come from different categories. So if you have 2 scenes and we know that they belong on different sides, one's a left scene and one's a right scene, then you're going to be particularly interested in building a description that distinguishes between those 2 scenes. And I've intentionally hedged here by saying adjacent, and I mean both spatially adjacent if those scenes are located in comparable positions within their categories, or I could also mean temporally adjacent, that one is presented right after another. And we've done both of those kinds of manipulations with subjects. Okay, so here's making the first point about how you could get contextualized interpretations for a particular scene. And maybe I'll give you a working example of this in a bit. So here, the rule could be that all the left scenes have a triangle above a rectangle, and all the right scenes have a triangle to the right of the rectangle. But there is a little bit of ambiguity because this scene over here is interpreted as a triangle being above the rectangle, but Paths is smart enough so that if we moved exactly that same scene over to the other side, then it would take that same scene and it would now still interpret it as a triangle being above a rectangle. So it can solve the same Bongard problem, but in order to do that, it's going to have given different interpretations for that same scene. It's either going to be interpreted as above the rectangle, or it's going to be interpreted as being to the right of the rectangle, depending upon whatever will allow the system to create a single rule that will distinguish all of the scenes from one side from the other side. Okay, here's a high-level overview of the architecture of Weitnauer's path system. And it's a probabilistic system. It'll come up with different rules at different times. The kinds of things that it's doing is very often it's going to be perceiving a feature on a target object. It's going to identify an object within a scene, and it's going to select a feature. So it might select the feature high for a particular square that it has noticed. And how it's going to be perceiving these features is definitely going to depend upon the other features that it's noticed in other scenes. And on the basis of these noticings, it's potentially going to create new hypotheses. And once a hypothesis is created, it's going to then be checked on other scenes that belong in the same category, other scenes that it's paired with. So one thing that happens is paths is oftentimes going to be getting pairs of scenes presented to it at the same time. And once it notices something in one scene, then it will tend to try to notice that same thing of another object in the other scene. And if those scenes belong in different categories, great, then maybe you would expect that it won't be found in the other scene, because that will give you a possible hypothesis for what distinguishes the scenes. If the two scenes come from the same category, then you'd expect that you'll get more excited about the hypothesis to the extent that that hypothesis is confirmed in all of the scenes that belong in the same category. And so this is one way in which the pairing of the scenes is going to influence how you're going to be developing your hypotheses. And another important kind of process that PATH engages in is recombining hypotheses, where it's going to probabilistically select two hypotheses and it's going to either combine their features or it's going to adjust a relation. And then on top of that entire loop, you're potentially going to be advancing to look at another scene pair. You may try to create a lot of different features that are shared or not shared between the paired scenes, but then you're also going to be eventually moving on to try to extend your hypotheses to cover others. Okay, so maybe at this point, I'm going to give you a live demo. So this is all something that you can access. I'll give you the link later on, but it is this link. I'll put it in the chat window. So we've preloaded paths with a bunch of physical Bongard problems that we give our humans as well. But you also have the ability to create your new own unknown Bongard problems. And this is something that I don't think I've seen in any other system that tries to solve Bongard problems, is the ability for people to create their own. So I think that's exciting. The input representation for paths is SVG, scalable vector graphics. So it comes pre-articulated with particular objects that have particular colors on them. So that is not part of the problem that paths is having to solve. It does not solve, for example, the figure ground segmentation problem. It knows that there is a circle that has a particular size, radius, a particular position in the scene. Okay, so when you run a model, and I guess this particular problem is very easy, and you can see that paths comes up with it very quickly. But you can see all of the different hypotheses that it was entertaining. So the final conclusion that it comes up with is that only in the left scenes does there exist one object, whereas in the right scene, the count is higher. It's actually two, but we actually didn't ask paths to come up with rules for both sides of the problem, but it suffices if it comes up with a rule that handles all of the scenes on one side and none of the scenes on the other side. Okay, so this would be considered a simple problem for paths. And you can see some of the hypotheses that it's creating along the way. The L means that this is an hypothesis which applies to the left scenes. R means to the right side. It could be both. Hypotheses are formed using one of three quantifiers. E stands for there's exists. so it's an existential quantifier. There's also a universal quantifier, which is all. So like all objects on the left side scenes are squares, would be an example of a universal quantifier. And we have another quantifier, which is a uniqueness quantifier. There's exactly one object on the left side, which is a circle, for example. The other information on the hypotheses is the confidence in the hypothesis on the far right side. And we also have the number of scenes that has been checked by the physical Bongard problem checker. So let me try to give a harder problem. Okay, yeah, I like this one. So as you see it move along, there's other things that you should notice. One is that it's always pairing the comparisons. And in this case, we force the comparisons so that it goes through and it only makes, in this case, between category comparisons. So it compares these upper left-hand corner scenes, and then it compares the upper right-hand corner scenes, and then it goes through. But in this case, we've sort of prearranged an order, a sequence with which it's going to be looking at the scenes. For other like human experiments, we'd be very interested in the comparisons where they're within scene comparisons versus between scene comparisons. Okay, so that's how PATHS is working. Other things to notice about this, if you're fast, is you can see it running simulations, perhaps. So what it is able to figure out in this case is that the objects will end up being together on the left scenes, and they'll end up being separated on the right scenes. Okay, and so you can run individual simulations if you want. You can start them all over, and you can run a particular simulation, which is what PATHS is doing much faster, so that it might have been hard for you to see. That is the kind of simulation that it's able to run to say that there is this connected relation, or there's a close-up relationship. Any other things I want to point out? Okay, so I want to point out that these hypotheses can be recursively embedded in each other. So the correct way to read this third hypothesis is, on the right side, there exists objects that are to the right of, and then you have another selector which is embedded in that, which is something like an object which is single at the end, which is by itself at the end. That's what single means here. The other thing to notice about PATHS is that it has a bunch of features and relations which it is noticing of these objects, and these are going to be changing in their importance over the course of solving a problem. If PATHS begins to think that stability is very important, then it will upregulate the importance of noticing stability in other scenes. The other thing to notice is that you can change how important a particular feature is. You could give PATHS a benefit by giving it a hint to say, I think that farness is important. And so you can clamp farness so that it becomes an important feature. Okay, so going back to, maybe the other thing that I should point out, just so that you know how to create your own problems and how to try these, is, that's not what I wanted. Here's a particular problem, and I've created on the side a bunch of SVGs, and you can change a problem just by dragging from your file. You could drag different images over, and that was probably done too fast for you to see, but I actually changed this problem so that the same scene is going to be interpreted as either two objects being close in the first situation or two objects being far from each other. And this is exactly that context dependency that we were talking about before. So I definitely encourage you to play around with it, to try to break paths. To be honest, it's not too hard to break paths. It's there's going to be situations where you think that it should be able to come up with a solution that you can come up with, and it won't be able to come up with it. And that's why it's only paths 0.7 rather than 1.0. One of the points I wanted to make is that the physical simulations allow paths to have a sensible understanding of a lot of concepts by running counterfactuals. So in paths, it has a working procedural semantics for the notion of what stability means, because it runs initial configuration in different initial randomly jittered, randomly moved ways. And what it sees is, would the end state substantially change if we had different random small difference starting configuration? What supports means for paths is that if a particular object were removed, would another object's end state change? So if C were removed in this particular scene here, then would that cause a difference to B's end state? The answer is yes. And so that is one notion of supports within paths. And it has ramped up different ideas of what supports means. So A is supporting B in this case, but only when we inject a bit of randomness. If we jostle around the system a little bit, then we see that B's position would change if A is and is not present. Another thing to point out is like predicates like free to move. These are very easy for people to see that the circle is free in the first two cases and stuck in a way in the second two cases. This is also something that paths can detect. And the way that it gets there is it imagines counterfactually a fragile string which is attached to a particular object like the circle. And if that object is moved in all of the different directions that it could go, would that object stay where it is? And the answer is no in the case of the free objects. It's able to move freely. So that gives you some idea of some of the predicates that apply. Here are other predicates, relations, and attributes that paths is able to implement. It doesn't implement everything that you might want. It doesn't implement everything that is implemented in the way that you might want. So this is definitely a work in progress. But it gives you, I think, to me, sort of this exciting idea that you can put in your own procedural semantics for a new idea that you have. And as long as you can construct it and understand it in this physics engine, then you give paths a new ability to see something that it hadn't seen before. A very important idea in paths is the idea of groups. So it sees groups of objects just like you and I would. So it would see like a tower or an arc. And one of the reasons why it's able to see these groups is because of these selectors. So it can select a bunch of objects on the basis of them occupying a particular part in space, but also on the basis of them all being white or all being triangle. So selectors are able to group not just upon spatial proximity, but on any kind of similarity between attributes. Okay, so we have done, as you might think, the natural thing of comparing how difficult a problem is for paths versus how difficult it is for humans. And what we find is that there is a pretty robust correlation, highly significant correlation. In this case, difficulty involves both the time that it takes to find the solution, the number of actions in paths that need to be executed before it finds the solution on average. And for humans, that's just response time. But also we look and we factor in the actual solution rates for the problems. And we've created problems that paths cannot solve. For the ones that we've created, it's solving about 45% of them, which is actually not too different from the rate with which people solve these problems too. There is one noticeable outlier. This is a problem that's really easy for humans to solve, really hard for people to solve, and it's actually the problem that I just gave to you before. People have no trouble seeing that the circle is free to escape on the left scenes and the circle is stuck on the right scenes. And paths can create it, but it's a very elaborated concept for paths. It has to have a lot of selectors built up before it can create the hypothesis, which captures that same idea. It doesn't have a pre-configured predicate for the idea of free versus stuck. The correlation's even a little bit better if we just look at the time that it takes humans to solve the problems, compared to the number of model actions that path requires. And a lot of what I'm just giving you a kind of a hint for what we've done in lots and lots of experiments. We're interested in the role of comparison, which is, I guess I say, that's why I think this is an analogy talk. So there's a deep sense in which paths does all its works without creating any analogies. And maybe you can pile on me at the end for that. But we are very interested, at least in the process of comparison. And we've done various manipulations for both humans and people where we change how easy it is for people to make different comparisons. And maybe you can imagine the 4 different Bongard problems that I'm showing here. You can see that they differ in terms of how similar are the objects that belong within a scene and, I'm sorry, within a category and between categories. So like, these problems are similar to each other and they belong to the same category. And also, if you look across the row, we see that the problems are similar to each other even when they belong in different categories. But we can shuffle that around as we see fit. So we can make it so the objects that are within a category are dissimilar to each other when they're close to each other. But we can still make it so that the objects that are between 2 different categories, but are easily compared with each other, are similar to each other. And so what we find, and this should probably be intuitive for you, is that it's really good if we temporally or spatially pair objects between 2 different categories if they're similar to each other, because that's going to help people zoom into exactly the critical feature which distinguishes them. And something which is very hard for people is if you have problems that are similar to each other, but they come from the same category. And the reason why this is hard is because people are going to come up with a lot of hypotheses that are wrong. People are going to think, oh, you have a whole bunch of objects that are varying in their height, that are all touching each other. And that doesn't actually have to be the case. But if you're just doing that comparison between those 2 scenes, you might get that idea. So similarity works very different when it's within and between category. And that's true for both the model and for the people. So the humans are on the left, paths is on the right, but you get this idea that between category similarity is it's better to be dissimilar than similar. I'm sorry, similar than dissimilar, but for the within category similarity, it's the opposite. So descriptions are best inferred when dissimilar scenes from the same category or similar scenes from different categories are going to be presented together. Okay, so I'm just wrapping up here. So what I'm taking as the core theoretical commitments of paths, first, that scene descriptions have to be continually created even as the concept rules are being constructed. It'd be convenient to first be able to create the descriptions and then try to come up with the concept rules. But there's lots of reasons for thinking that's going to be very inefficient. You won't be able to sail between the Scylla and Charybdis of having too many features that you're going to be created and having just the right features that you want to create. We talked about 3 different ways in which the context is going to be influencing the descriptions. Context defined by the pair you're comparing, by the rest of the scenes that you're comparing, and also you have a within scene context. So new descriptions are coming from perception and these physical simulations. And it's not just a result of combinations. And in that way, I would be comparing what we're trying to do with what a lot of the work on constructive induction was. And I think what we're trying to do is much more in the spirit of Shimon Ullman, the elder Ullman, when he was talking about visual routines. We're talking about these visual spatial routines for detecting relations like support and stability. In this world, creating perceptual groups is very important part of paths, and creating focused objects. But we also do share a lot of commonalities with the new Bayesians. We are like Piantadosi, I'm having in mind, and Charles Kemp, Tom Griffiths, Noah Goodman, where we are very interested in creating rules composed from a recursive grammar. And in that way, what we're doing is pretty different from a lot of what goes on under deep learning, although deep learning is a broad category. And so there are people very interested in relation learning within deep learning as well. Thinking of concept formation as an open-ended search of compositions, I think is important if we're trying to model the creativity that humans show. We're very interested in reproducible, testable code that you can try out your own problems with. So that's the link that I just sent you in the window. And so I'd like to stop now and open it up for questions. Thanks.